Welcome to another episode of Game Theory. Today we are in Chapter 12, looking at evolutionary games. So while ecologists were applying game theory to study things like firms and competition, it turns out that biologists were also studying game theory. They look at game theory as a way to model interaction between species, or also interaction within a species where there are different types of genes. So the progress in the research went on largely separate paths. In economics, we talk a lot about Nash equilibria. Biologists developed their own notion of equilibrium, and it's actually fairly similar to Nash equilibria. We'll see some of that overlap in this chapter. So here we'll take a brief look at what were the biologists doing in game theory and see how similar and how different it is with economics. So the way biologists look at game theory, they say that the genes create a certain type of species. They call it type the genotype. So maybe your genes might make you inherently more cooperative, for example. So those differences in genes then manifest themselves in behavior. So the actions that arise because of your genes, we call it your phenotype. It's analogous to a player's strategy in game theory. So, in my example, I said perhaps your genes make you predisposed to be more cooperative. As a result, if you have those kinds of genes and you're playing a prisoner's dilemma game, you end up playing not confess. So those genes, the genotype, leads to the action of not confessing the phenotype. So in the language of economists, we say the player played not confess. We say not confess is their strategy in the game. But our biologists call it the phenotype, the manifestation of their genes. So in economic game theory, we talk about payoffs. In evolutionary game theory, I talk about fitness. So the idea is that if you're successful in some game of biology in the real world, that's going to make you more likely to survive, more likely to pass on your genes. So types with a higher fitness are going to eventually increase their share in the population. So let's go back to our prisoner's dilemma example. I said perhaps your genes make you more cooperative as a person, and that can result in you playing not confess in prisoner's dilemma kind of environments. So perhaps that cooperation helps you out in society and makes you more likely to survive and reproduce. And that can mean there'll be more cooperative types in the future. Alternatively, maybe the cooperative types who are playing the not confess may just get exploited by people who are more self-interested, and then the more self-interested folks become more fit, and they end up driving out the cooperators. So one issue where economics and biology differ is that in biology, we don't just look at what is the equilibrium, but also look at is an equilibrium stable. So here's what they mean by stability. So if a number of people who are a certain type, if that changes a little bit, do you go back to the same equilibrium, or do you drift off to some different equilibrium? So it could be there could be a mutation. So maybe one of the A types somehow becomes a B type, or perhaps so a bunch of A types in one region and some B type from another region migrates, and we got to find out if we're going to go back to being all A types or there's going to become a mixture of A and B types. So I'll go show you guys some examples where you can see how you can conduct that analysis. So our first example, I kept talking about the prisoner's dilemma game, so let's use that one. So in our previous chapter, we also talked about collective action. We said one way to model a group project at school is as being like a prisoner's dilemma game. You can see why that might occur. So if you guys are working together as a group on some project for a class, cooperative outcome is you all work together and put in your best effort and make the project a success. However, that might not be the dominant strategy. It might be dominant strategy that everyone slacks off as a free rider and the project goes poorly. One way out of many to model interactions in group projects. So, looking from a biology perspective, we're going to say that rather than choosing to work or not work on a project, it's more like your genes dispose you to being hardworking or your genes dispose you to be lazy. So, we'll say there are two types of students here. I should say on two genotypes. And the behavior comes in to phenotypes. So I'll call the lazy types L types. And because of their genes, they just don't work hard on a group project. You tell them this project is really, really important. They don't listen because that's just not their nature. Another type we'll call them responsible types, or R types for short. And these guys will put in the hours to make that group project a success. So we'll look at the fitness, or rather the payoffs in economic language for the game. So let's say we have the responsible types up here, and here are the lazy types. So if two responsible types are assigned the same project, let's say fitness is -1. If two lazy types are working together, they both don't work, so the project goes badly for both of them. If you have one responsible type and one lazy type, the lazy type benefits from the responsible type's hard work, so it's a good grade without putting in effort. Responsible type also gets a good grade, but they do double the work, so they're really unhappy about that. -20 for them. So let's say that fraction PR is responsible, which means that 1 minus PR is going to be lazy. So to keep things simple, we'll start up looking at there's just the same kind of species, students in this case, who come in just two types. Later I'll look at more complicated cases where two different species, and each species can have two different types of their own. So the first thing we do is to look for candidate equilibria. So one equilibrium could be is that maybe they're all R types. So PR would be 1 in that case. Other option would be they're all L types. PR means 0 in that case. Alternatively, there could be some mixture where there's some fraction of R types and the other fraction is L types. So maybe the equilibrium could be possibly they're 60% responsible types and 40% lazy types. Just beat the number up entirely. We gotta do some math to find what exactly are those equilibria. So I'll call it potentially still because we haven't actually investigated stability yet, so it's all potential right now. you make the connection to economic game theory. So it's like all R types or all L types, that's analogous to playing the same strategy every time. That sounds a lot like a pure strategy in Nash equilibria. Like in the Prisoner's Dilemma game, confess is always the Nash equilibrium. You never want to randomize, so that's the connection there. Now here, some types are responsible types, some types are lazy types. That's analogous to a mixed strategy Nash equilibrium, where sometimes you play one strategy and other times you play the other. So you can see it while economics and biology went on different tracks, they nevertheless coincided on some common ideas. So our mission here is to find what is that mixed equilibrium. We call that, for terminology, we call it a polymorphism. So there are two different types of the same species that can coexist in this one. We call these ones over here monomorphisms because in that case there's only one type that survives in equilibrium. So we're going to try to find the polymorphism, or if you're more familiar with, the mixed strategy Nash equilibrium. So it's a 2x2 game. You already know how to find the mixed strategy Nash equilibrium there. So what we do is we find the expected fitness of each type. So here I'll first find what's the expected fitness of an R type. So I'll call it EFR. So let's look over here on our table. So here's an R type. With probability PR, they meet another R type, and their fitness in that case is -1. With probability 1 minus PR, they meet an L type. That means our responsible student puts in all the work, and they don't like that. They get -20. What does that come out to? So we have -1 PR. And then we have -20. If we distribute this through, plus 20 PR. Combine these guys and you get -20 plus 19 PR. Now let's do the same calculation for the L type. So if you're an L type over here, oh, there's a typo. That should be 1 minus PR. If we had been in a live class, one of you guys would have caught that several minutes ago, but we're not, so might be catching those errors a little bit slower than usual. All right, so if you're an L type with probability PR, you run into an R type. Good news for you, you can slack off and still get a good grade because they do all the work. So your fitness is 0, multiply by probability PR. With probability 1 minus PR, though, you run into another lazy type. Both you guys don't work, so your fitness will be minus 12 because you both get a bad grade. So this just goes away because 0 times PR is going to be just 0. This will become minus 12 plus 12 times PR. So to find a polymorphism where both L types and R types coexist, we got to look at which value of PR are these two fitness levels equal. So we set them equals to each other. So this is very much like using the opponent indifference property when we were doing mixed strategy Nash equilibria. So what is that going to yield? So let's push the minus 20 over here. So we're going to get minus 12 plus 20 is going to be positive 8. Then I'll push the 12 PR over there. So I get 7 PR. And now we'll divide both sides by 7 to isolate, or perhaps I should say these days, to quarantine the PR. So PR is going to be 8 over 7. Well, that's a problem. Remember, PR is the fraction of the population that is R types. So in order for both types to be equally fit, you have to have more than 100% R types. So that's just not possible. So in this game, group project as a prisoner's dilemma, there is no polymorphism. There is no equilibrium where both types can coexist. So what happens here is that the lazy types always get the higher payoff or higher fitness. So when we can do our analysis is that we've done our analysis for the mixed equilibrium, show the mixed equilibrium does not exist. You also have to analyze the two other equilibria, the monomorphism. So those ones that are all R types or all lazy types. So you can do that with a graph. So in my graph, I'll put PR over here on the x-axis, proportion of responsible types, and then I'll have the fitness levels, which I'll call F, on the y-axis. So for the responsible types, our intercept is negative 20, and our slope is positive 19. I guess we're going to be way down here in negative territory. So I'll call it FR for the responsible types. Now for the lazy types, the intercept is minus 12, which is a higher intercept. That's going to be somewhere hereabouts. The slope is somewhat shallower at positive 12. So that's going to look something like this. So we established that the fitness levels are equal when PR is 8/7, which is going to be out here. Those are the two lines intersect. The problem now is that PR is a probability, so that's going to be bounded between 0 and 1. So you can see on our graph, but if I got a different color out, that the lazy types always have higher fitness. At least when you're in that range 0 to 1, which you have to be in because PR is proportion. So here's how you can do your stability analysis. In this region here, L types are always fitter. That means that the L types will get to survive and pass on their genes. The R types, on our hand, are going to die out. So what that's going to mean, PR is the fraction of R types. That means PR is going to go down. So we'll draw arrows showing PR decreasing. So what does that mean for our two other equilibria? Well, we have one equilibria that's going to be all R types. So PR is 1. Like I said, the monomorphisms are all the same type, so all R types. That one is going to be unstable. So for stability, we look at if the proportion changes just a little bit, do you go back to the same equilibrium or do you go somewhere else? In this case, we start out with PR being 1 and PR drops just a little bit. Then you just follow the arrows. The arrows say that the L types will increase and PR is going to decrease, so that's going to take you further and further away from the equilibrium. And why PR could fall, there could be migration from another population, a different region, or there could be a mutation. Either one could cause PR to go from, like, say, 1.0 to 0.99. So that equilibrium is unstable. We established that there is no mixed equilibrium, there is no polymorphism, so you can't have a fraction, you can have a proportion be 8/7. So the last possible result here is the other equilibrium where PR is 0. So if PR is 0 means everyone's an L type, that's going to be stable. You can see if you change that fraction just a little bit, let it go from here to there, the arrows push you back. So if some R-type goes and tries to migrate there, the R-type's going to be less fit, so the R-type's going to die out, and will go back to being all L-types. So that's stable. So, for some terminology, we'd say it's an evolutionary stable strategy, often abbreviated as ESS. So the other equilibrium, PR equals 1, it still counts as an equilibrium, it's just not stable. Now this brings us to another comparison of biology and game theory. So we established that the only stable outcome, evolutionary speaking, is all L-types. Well, if you compare it to what we know from game theory, perhaps that really should not be a surprise. I already said in the Prisoner's Dilemma game for a group project that not work is a dominant strategy. So it turns out that a dominant strategy is always going to be evolutionarily stable. So even though economics and biology went along different tracks, they somehow got some of the same conclusions. So that's one way to look at one example of evolutionary game theory. Come back for our next episode and we'll look at some more examples.